Today we are putting on our detective hats. We're going to crack the code on what really makes software fast or painfully slow. And here's a hint. It has almost nothing to do with how powerful your computer is. All right, let's jump right in. So let's kick things off with the central mystery. How is it possible that for the exact same problem, one solution can finish in the blink of an eye while another one might take, well, longer than you have? Secret isn't in the hardware, not at all. It's in the method, the fundamental design of the algorithm itself. You know, to compare these methods, we can't just pull out a stopwatch. I mean, running code on a supercomputer versus a 10-year-old laptop, you're going to get wildly different times. It's not a fair comparison, so we need a universal measure. Instead of seconds, we look at the rate of growth. In other words, how does the work scale as we throw more and more data at it? And that brings us to our first huge concept, time complexity. This has nothing to do with seconds on a clock. It's all about counting the number of operations. See, we ask questions like, if we double the input data, does the number of steps we have to take also double? Or does it maybe quadruple? Or does it barely even change? That relationship is what it's all about. Now the other side of this coin is space complexity. Performance isn't just about speed, right? It's also about how much memory, or RAM, an algorithm eats up. This includes the obvious stuff like variables and arrays, but also the memory needed to keep track of function calls, something we call the call stack. And just like with time, we're measuring how that memory usage grows as our input, n, gets bigger. So let's get into the fun part. You see, algorithmic complexity leaves behind these really distinct patterns. Think of them like fingerprints at a crime scene. We're about to learn how to spot the most common ones you'll find out in the wild. Okay, this right here is the hierarchy you need to know. It ranks the common complexities from the absolute best at the top to the catastrophically bad at the bottom. At the very peak, you have the lightning-fast constant time, O1, followed by the super-efficient logarithmic time, O log, and then you get the very common linear time, ON, a key one for sorting called ON log n, and then we start to slow down with quadratic ON squared. As we go further down, things get slow fast. And this chart shows you exactly why that hierarchy matters so much. Just look at that. Linear O of n grows in a nice, predictable straight line, but look at O of n squared, and especially O of 2 to the n, they just explode. A tiny increase in the amount of data can send the runtime into the stratosphere. Honestly, choosing the wrong algorithm here can absolutely tank your performance. Let's start with the best of the best, O of 1, or constant time. This is pretty much the holy grail of efficiency. It means your algorithm takes the exact same amount of time and space, no matter how big the input is. Think about accessing a single item in an array by its index. It's just one step, whether the array has 10 items or 10 million. Next up, ON, or linear time. This is super common, and for most things, it's totally fine. The workload grows in a straight line, directly proportional to the size of your input. So if you double the data, you roughly double the time. The classic example is having to look at every single item in a list one by one. Now we're getting into the really clever stuff. O of log n logarithmic time. This is where algorithms get incredibly powerful. The whole strategy is divide and conquer. You know, imagine looking for a word in a dictionary. You don't start at the letter A and flip every page. No way. You open it to the middle, and instantly you've thrown out half the book. With every single step, you cut the problem in half. And here we have O of n squared, or quadratic time. This is often where performance bottlenecks start to pop up. It usually happens when for every single item in your data, you have to go and compare it to every other item. The classic code pattern is a loop nested inside another loop. The work grows exponentially, and it can get really slow really quickly. Okay, detective, you've learned the fingerprints, so let's move on to the investigation phase. Now we're going to learn how to spot these complexity patterns right there in the code itself. All right, here is your first and most fundamental rule. If you see a single, simple loop that goes from 1 to n, your first instinct should be linear time. ON, it's that simple. And by the way, in terms of space, this loop just needs one little variable to keep count, so its space complexity is constant, or O of 1. So what happens when you put a loop inside another loop? The rule is just as simple. You multiply their complexities. If you have a loop that runs n times and inside of it is another loop that runs n times. You get n times n, that's O of n squared. This is the absolute classic signature of quadratic time, and if you had 3 nested loops, you guessed it, O of n cubed. Okay, but what if the loops aren't nested? What if they just run one after the other? In that case, we add their complexities. So an ON loop followed by another ON loop gives us ON plus n, which is O to n, but, and this is key, in complexity analysis, we ignore constant factors like that too. We're only interested in the dominant pattern of growth, which is still linear. So O to n just simplifies right down to ON. And hey, remember our dictionary search. The whole idea was cutting the problem in half over and over. Whenever you see a loop with a main variable as being divided by 2 each time, or maybe even multiplied by 2 until it reaches some target n, that is the unmistakable fingerprint of logarithmic time, O of log n. All right, let's add a little bit of nuance here. The very same algorithm can actually perform differently depending on the specific data you feed it. And this brings us to the really useful concepts of best, worst, and average case performance. And here's the formal language for that. Now, you've probably heard me say big O a lot. And while people often use it as a general term, it technically refers to the worst case scenario, an upper bound on performance. For the best case scenario, we use big omega. And when the best and worst cases are actually the same, we can use big theta to give a really precise description, a tight bound. A simple linear search is the perfect way to see this in action. I mean, what's the absolute best thing that can happen? You get lucky. The item you're searching for is the very first one you check. That's a best case of omega of 1. And the worst case, of course, it's the very last item in the list, forcing you to check all n items. That's a worst case of big O of n. Now it's time for the golden rule. This is a crucial trick that simplifies almost all complexity analysis and helps you get to the right answer fast. This is the one principle that ties everything together. Here it is, the dominant term rule. When you have some long, complicated expression for the number of operations, you find the single term that grows the fastest and you just drop everything else. That's it, all the constants, all the slower growing terms, they just vanish. Let's see this in action. It makes it so much clearer. Let's say your analysis shows an algorithm takes 3n squared plus 2n plus 5 steps. Okay, apply the rule. What's the fastest growing part? Well, it's the n squared term for sure. So we drop the constant 3 in front of it, we drop the slower 2n term, and we drop the plain old 5. The entire thing simplifies right down to O of n squared. Why? Because as n gets really, really big, those other terms become so tiny in comparison that they're basically irrelevant. So why did we just go through all of this? Because understanding this stuff is absolutely fundamental to building good, robust software. It's about scalability, making sure your app doesn't fall over when it gets popular. It's about efficiency, choosing the right tool for the job. And let's be honest, it is absolutely critical for passing technical interviews and exams. So there you have it. We've given you the detective's toolkit. You can now spot the fingerprints of inefficiency and you understand the language of performance. The only question left is, where are you going to point your magnifying glass first? What hidden ON squared loop are you going to go hunt down and optimize?